Hi guys, good morning. Is everyone ready? Shall we start? Hello. Guys, are you able to hear me?
Yes, sir.
Okay, cool. Right. So yeah, we are at the last part of this chapter. It's a big chapter, isn't it? Right. But this chapter is the basic foundation of all other, like I would say, not all the other chemistry chapters, but still, if you don't, this is the mole concept, atomic structure, periodic table, chemical bonding. All these are so much fundamental chapters if you want to venture into chemistry or even for your exam point of view, right? Everything is very important. You understand, right? Whatever you have studied in your 11th, like say in your 10th class, that is nothing. What you're learning here is really in depth, going into molecules, how the electronic structure is, how the configuration is, all that, right? So we are at the last part of this chapter, right? And we are going to see. Oh, so guys, did we see Fajon's rule? Right? I told you about. I think last class we discussed a little bit about dipole moments, bond angles, and then we went on to see covalent character and ionic compounds, right? So we saw how is it happening. There was a phenomenon called as polarization, right? So polarization is a phenomenon where the electron cloud of the anion gets distorted, right, because of the cation, right? So I talk in terms of polarizing power, in terms of cation, and I speak of polarizability in terms of anion, right? So whenever polarizing power or polarizability increases, the covalent character also increases. And then we saw for cations, the size and your polarizing power are inversely related, and charge and polarizing power are directly related. And for anions, we saw size and polarizability are directly related, and charge and polarizability are directly related. Right? So this is what we saw, and then we saw some examples also how the ionic character will vary and all that. Right? Okay. So yeah, so that's it. That's about Fajon's rule and covalent character and ionic compounds. So we'll move on. Right. Okay. So guys, I have to go back to your atomic structure for this particular concept which you're going to see. Right. So in atomic structure, the last atomic model, that was quantum mechanical model. Hope you remember who gave that theory. It was Schrodinger, if you can remember. So there only we saw quantum numbers. We saw that there was this psi. Hope you remember, right? So this psi was talking about the probability. I would say psi as such doesn't have. It's called wave function, isn't it? The psi is what is called as wave function. So this is for different orbitals. For s orbital, this psi will be different. For p orbital, the psi will be different. So on and so forth. So if I square this function, I hope you remember this was a function, not a value, like a sine, cos, tan, like that. This is psi of x, basically. This is a function, right? So now this as such doesn't have any physical meaning. So what I said is, if I square this function, if I write psi squared of x, I'm going to get the probability of finding the electrons, isn't it? So which place, if I apply this particular function to a particular space, like particular constructed volume, so in that volume, if I apply this, I will say that, okay, 60% chance that I'll be finding electron there, or 70% chance that electron might be there, right? So all these things were what we studied in quantum mechanical model, right? And please understand that quantum mechanical model took it. That is the only model, I would say. In all, you have Bohr's model, you have after that like before that Rutherford's, before that Thomson's. All these things, you never took the wave nature of electron into the picture, isn't it? So according to de Broglie, hope you remember all these things. So according to de Broglie, right? So what he said, since nature is symmetrical, right, and so is light and electrons. Very simple statement, right? So we know good, bad, men, women, right, left. So all these things, the entire universe is symmetrical. Why not light? Why not electrons? They will also have symmetrical properties. That means they will have wave nature as well as particle nature. So then we went on to derive the de Broglie's wavelength and all that. So yes, so the thing is, your quantum mechanical model takes into account of two important theories, right? One is de Broglie's hypothesis. The other one is Heisenberg's uncertainty principle, right? So hope you remember what Heisenberg's uncertainty principle says. You remember the cat in the box experiment, right? So what I said, that cat was simultaneously dead and alive, and you will not be able to predict. You will be able to tell them, okay, 50% chance that the cat might be alive, there's a 30% chance that the cat might be dead. All this you'll be able to say, but you will not be able to say, sure, that the cat is dead, or say, I'm 100% sure that the cat is dead. We'll not be able to say, right? And this mechanical, the quantum mechanical model also is a probabilistic approach, right? We will not be able to tell with the help of this theory, that is the quantum mechanical theory, that okay, electron is going to be right here at this point. No, we will not be able to do that. We'll be able to get the probability, right? So this is in accordance with two very good theories, that is my de Broglie's as well as your Heisenberg's uncertainty principle, and the theory which you say the theory which we are going to see today is actually going to depend on this. Okay, so we are going into the wave nature of electrons, right? We are going to take not the electrons as such. I would say I am going to take the wave nature of the orbitals, isn't it? Guys, please understand that if I write s orbital like this, it is not like it is. This is the shape of the s orbital. It is the shape of the probability function. Basically, what I can say is this talks about the electron cloud, isn't it? This talks about the electron cloud, which is symmetric, right? Same way for p orbital is the dumbbell shape. Whatever I draw, it is not. What to say? It's actually wrong to call that is the shape of the p orbital. It's actually the shape of the electron cloud of p orbital. That is how it is, right? So, anyways, so what we are going to do is we are going to see this new theory called molecular orbital theory. Okay, this is what we are going to see today, right? Molecular orbital theory, MOT in short form, right? Okay, so what we're going to do here is, as I told you, I am going to take into account the wave function or the wave nature of the orbitals, right? And when you go to your 12th class, right, there'll be a chapter called as interference, like not a chapter, there's a concept called as interference. You'll be studying the chapter in wave optics. Okay, you'll be studying it, right? But anyways, since you don't know certain things here, I will be explaining you wherever it is required, the physics which is required. Right? Anyways, we'll see. Right. I would say this is similar to your theory of hybridization, right? Like what we saw, what I said in theory of hybridization, I said that two atomic orbitals are going to combine to form a hybrid orbital, right? So here also, I would say that two atomic orbitals will combine together to form a molecular orbital, right? Just the name is different here. There was hybrid orbital. Here it is molecular orbital, right? So two atomic orbitals are going to combine to form a molecular orbital, but there in hybridization, I told you it is a purely mathematical concept, isn't it? But here, I'm actually going to take into account your wave nature, right? Basically, I'm going to take the psi into the account, right? Like properly explaining, like going in depth and explaining this particular concept is out of the scope of 11 itself, right? But anyways, we'll try to see maximum whatever is explained here. Okay, right. So, okay. So let me put it like this. Let me take an example of a very simple molecule, right? So I'm going to take the example of H2. Okay, right, right. So I have two hydrogen atoms, right? So both of them are having 1s1, another is having also 1s1, right? So let me call the two hydrogen atoms as HA and HB, right? And I'll call the s orbitals of these two hydrogen atoms also as such. Say it's 1sa and 1sb, just for the notation, nothing else, just for the differentiation, nothing else, right? So we did this, okay? So in H2 molecule, right? In H2 molecule, again, we are not anymore going to speak about the pure atomic orbitals. That is, I really don't care about what is this oneness of the one other. I mean, first hydrogen and the oneness of the second. That is not what I'm going to see. I am actually going to tell that these two s orbitals are going to combine. Okay, now this combination is what is different here. from your theory of hybridization and your molecular orbital theory, right? So the combination here is talking about a physical phenomenon called as interference. Okay, we are gonna like it's gonna take into account this. It's basically the basic principle behind this. I would say is this interference. Okay, fine. So what is this interference? So basically, interference of the waves. Oh, I would say interference is nothing but it is the interaction of two waves. Right? This interference is nothing but it is the interaction of two waves. So what is going to happen here? I am going to have some kind of wave associated with this oneness. I'm going to have some kind of wave associated with this oneness. One is A and one is B, right? So they are going to combine together. They are going to form a new wave, right? They will combine together. These two waves, I'll tell you how they combine, don't worry, right? So for now, please understand that the wave corresponding to one is A and one is B are going to come together, combine together to form another wave, right? So that another wave will again correspond to some orbital, and that orbital is what is called as your molecular orbital, right? So again, how will I put it in a nutshell now? The pure atomic orbitals will have their own waves or say wave functions, right? So these pure atomic orbitals, these waves will undergo interference to form another wave, and obviously that wave will correspond to one more orbital called as molecular orbital. That's very simple, right? Okay, so now we have to see what exactly is this interference, right? So we'll look into it, right? So we'll come back to this again. Don't worry, this hydrogen molecule will again come back. But yeah.
So, sir, can you just explain it again, sir? I had connectivity issues, so I wasn't able to hear properly.
Yeah. Sure. So what I was telling is, so we're talking about this H2 molecule, right? So what I'm telling is, I have one s orbital for one hydrogen, another one s for another hydrogen. So we already know from the quantum mechanical theory that all the atomic orbitals will have their own type of waves. They are nothing but the wave function. They are in the form of waves, right? So what I'm going to tell you is, if at all these two orbitals are going to combine, the orbitals in the sense the waves are going to interact, right? The waves are going to undergo interference. Which two waves? This one is A waves and one is B waves are going to interfere. That is, they're going to interact, and they're going to form sorry, and they're going to form a new wave, like two waves combined together to form a new wave. And that wave again will correspond to your another orbital, and in this case it is not a pure atomic orbital, it is going to be called as a molecular orbital for H2. That's what I'm saying. Did you understand?
Yes, sir. Yes, sir.
Okay, so don't worry, we're just starting here. You will get to know all the things, right? So we'll see what exactly is this interference, and we'll come back to this H2 molecule. Right. Fine. Say, assume that I have one wave like this, some wave, sine wave. Say I have another wave. Okay. Fine. Now, please understand this interference, or say the way in which the two waves are going to interact, can be of two types. Or in a nutshell, I can tell that interference itself can be of two types, right? Say one is what is called as constructive interference, and the other one is what is called as destructive interference, right? Constructive interference and destructive interference, right? So we'll see what exactly is happening here. Fine. So if I look at this case, right? So I'll assume that I'm going to add these two waves. Like these are going to add together. These two waves are going to add together, right? So what will you expect? So this part will get added, or we'll say this is part one, part two. So what you see is this one and one will make a bigger wave if I am adding them together, right? So can you see that this one will actually combine with this one and form a bigger wave, bigger part of the wave, and this two will combine together to form again a bigger part of the wave. So I will be expecting something like this. I can expect something like this. Is it not? These two had combined together to form this wave, right? So this wave again will obviously will correspond to some other orbital, and that definitely we know that it is going to be the molecular orbital, this wave. Okay, so this is one way of combining. Okay, now what if I had one wave like this, I have another wave like this. Now look at this, right? So in this case, if they interact, right? In this case, if they interact, what is going to happen? You see that here from 0 to some x value, say I assume this is some x value, right? So 0 to some x value, it is on the positive side. But here again, if I take the same x value, 0 to x, it is on the negative side, right? So now what will happen? Now if this and this will interact, right? If this and this will undergo interference, I am going to form a smaller wave. Okay, obviously it can be even 0 if the amplitude here and the amplitude here is same, right? Because this will get exactly cancelled by this, right? But we'll not look into that much depth. So please understand that if this and this and this and this will combine, they will form a smaller wave. Say I would say that they will end up something like this, very small. Okay, so now the first case what you saw is what is called as your constructive interference, when the say now in a wave there are little technical terms which you have to know. So this particular part is what is called as your crust, right? And whichever is below the origin, below the axis, is what is called as trough. Hope you know all this crust and trough. Crust is the maxima, trough is the minima, right? So if you see that in like you will see that in constructive interference, the maximas will act together, the minimas will act together to form a bigger, right? And in your this now in this case, this whatever the second case we saw is what is called as your destructive interference, right? So in destructive interference, maxima of one wave and the minima of the another wave will combine, right? Maxima of another wave and minima of another wave will combine to form a smaller wave like this. Now in this case, in the last case, I formed a bigger wave because of constructive interference. Okay, now this exact same thing is what is going to happen in your orbitals also, because orbitals are also going to have some wave functions. They will undergo constructive interference, or they might undergo destructive interference to form another wave functions. That wave functions or waves will correspond to molecular orbitals. So these two, say if I this and this, will actually correspond to some molecular orbital. Okay, right? Cool. So we understood this constructive interference and destructive interference. Okay, now we'll go back to your H2 example. We'll take again HA and HB and we'll see what happens. Right. So guys, any doubts till now? Is it okay? Shall we move on?
Sir,
Yeah.
in case 2, the maxima and minima subtract, no, sir, from.
Subtract, yes.
Okay, sir.
Like you can even put it like this. See, how to put it? This way also you can represent, right? Now in this also I will be able to represent destructive interference if instead of positive sign, if I put a negative sign, that again corresponds to your destructive interference.
Okay, sir.
Are you able to get what I'm saying?
Yes, sir.
Right? Or in this case, I can even put if I put plus only, this makes sense because anyways I'm going to have destructive interference happen because the waves are as such, right? So anyways,
Yes, sir.
like you don't have to worry this. Nobody's gonna ask you questions from this. Do not worry this, but this is required for your understanding, right? How molecular MOT works. This is the basic understanding, and you will study about this in depth in your physics, but not in 11th, but in 12th, wave optics, right? So you'll study about that. Don't worry. Right?
Okay, sir.
Cool. So what I was telling, yeah, we'll go back to your H2 example. Right. Say again, this H2 will have hydrogen, HA, and HP. It has one as A1, one as B2. Right. Okay. Fine. So let me talk in terms of wave functions here, right? So now how can I put it? So this will have a wave function of psi A, assuming, right? And say this will have a wave function of psi B, assuming, right? So now what is going to happen? Now they have to undergo interference, like maybe that means the waves corresponding these two has to undergo interference, right? And obviously I'm going to form H2 that will have a different type of orbital called as molecular orbital, right? So now how will I be able to write this? It's actually psi squared, right? We will not be able to do anything with psi A and psi B as such. We have to square these functions, right? But we will not square it and then add it. We will write it like this. Say for H2, if I have to write, it is basically going to be HA's and HB's wave functions squared, right? So I can write it like this. For H2, it is psi A plus psi B, the whole square. I can write it like this, right? Eventually, you want to square this function because then only you'll get the probability. As such, psi has no physical meaning. It's just a wave, nothing else, right? So I'm talking about this square of this. So I know what will I get? I'll get psi A squared plus psi B squared plus 2 into psi A psi B, right? So these are individual, this corresponds to the psi A squared and psi B squared corresponds to the individual atomic orbitals wave functions, isn't it? Like this psi A corresponds to hydrogen A and this psi B squared corresponds to Hb squared. That we are not interested in, right? What we are interested in is where the interference is happening, and you can easily see that there is interference happening here, right? The two waves psi A and psi B are combining, and that will have a different wave function, and this will correspond to the H2 molecule, right? This 2 psi A psi B will actually correspond to the H2 molecule, correct? Now I had only constructive interference happening. How will I be able to find out how constructive interference, how destructive interference? It is all going to depend upon what sign I took. So look at here. I added, that is psi A plus psi B. Now this plus indicates that it is going to be constructive interference, right? I can even put a negative sign indicating that it is going to undergo destructive interference, right? So in that case, what will happen? Say if I write psi A minus psi B, the whole squared, again, I know what will I get? Psi A squared plus psi B squared minus 2 into psi A into psi B. So again, you can see that here I'm going to have a negative sign indicating that it is going to have destructive interference. Understood? So the same wave functions will undergo two different types of interference, that is one constructive, one destructive, to form two different molecular orbitals. Please understand. This molecular orbital, this obviously this corresponds to a wave. This wave corresponds to an orbital, which is going to be called as a molecular orbital. So this molecular orbital and this molecular orbital are different because they are formed by two different types of interference, one constructive and one destructive. Okay, so accordingly, I'm going to give some names for these orbitals. But again, before that, so hope you understood what exactly is happening. If we took a very simple example of H2. Okay, and then we say that I have wave functions corresponding to it, so I squared it, added it with the help of plus and minus, constructive and destructive, so I got two molecular orbitals. Okay, fine. Now just like you had a rule in your theory of hybridization saying that the number of atomic orbitals combining, right, should be equal to the number of hybrid orbitals formed, isn't it? How did I say that? Say if at all it is sp hybridization, right? One s and one p will combine together to form two numbers of sp hybridized orbital. The number of atomic orbitals and the number of hybrid orbitals should be same. That was a very one of the main points, isn't it? Now the same point holds good here also, right? So please understand that the number of atomic orbitals combining will be equal to the number of molecular orbitals formed, right? That means if at all I have two atomic orbitals combining, I should have two molecular orbitals formed. Now we even saw the proof here, isn't it? What proof? I had two orbitals of hydrogen A and hydrogen B combining, one from each, right? So I found two molecular orbitals, one by constructive interference and the other by destructive interference. Right, so this also this point holds good here also, and obviously there in theory of hybridization also. Okay, right? Cool. Fine. Now we will see what are all the types of molecular orbitals I can have, right? So what are all the types of molecular orbitals I'm going to have? Okay, so we already know, right? Whenever I have constructive interference, I'm going to give you the names now, right? So whenever you have constructive interference happening, right? So obviously you're going to form a molecular orbital there. That molecular orbital is going to be called as bonding molecular orbital. MO represents molecular orbital, right? So whenever you have a constructive interference happening of two wave functions and you form a new wave function, that wave function is going to be called as bonding molecular orbital, right? Okay. Now whenever I have destructive interference happening, that is going to be called as anti-bonding molecular orbital. Okay, whenever you have destructive interference happening, it is going to be called as anti-bonding molecular orbital. Okay, and as the name tells you, right, whenever constructive interference happens, right, that is going to have bonding molecular orbitals. That means this particular interference or these orbitals will support bonding, right? And obviously anti-bonding orbitals are against bonding. They are unstable, right? So if I talk in terms of stability point of view, right? If I talk in terms of stability point of view, definitely bonding MOs are more stable than anti-bonding MOs, right? Or if I speak in terms of energy, right? Energy of BMO, that is bonding molecular orbital, will always be lesser than ABMO, that is the energy of anti-bonding molecular orbital, right? So I know that energy and stability are inversely related, right? Energy and stability are inversely related. So obviously my bonding molecular orbital is more stable than the anti-bonding molecular orbital, right? So even in the energy graph, if you see, the bonding molecular orbital will be lesser in energy than the anti-bonding. Obviously, I know Aufbau's principle. What does Aufbau's principle says? Aufbau's principle says the lower energy orbitals has to be filled first, and then only you have to go for higher energy orbitals. So if at all you're going to put electrons into this molecular orbitals, first they have to go to the bonding orbitals. Then only you can go for anti-bonding orbitals. Are you able to understand? And whatever the rules which you saw for filling the electronic configuration, I think you saw three rules. One was Aufbau's principle, Pauli's exclusion principle, and your Hund's rule of maximum multiplicity. All these three things should be followed here also. Again, I repeat, Aufbau's principle, Pauli's exclusion principle, and your Hund's rule of maximum multiplicity should be followed here also. Right? Okay. Now, okay, we understood these two are the types of bonding orbit. Types of orbitals, that is bonding MOs and anti-bonding MOs, right? But please understand, if two s orbitals combine, like say I saw in 1s orbitals were combining in H2, so I will form one bonding and one anti-bonding. Same way, if two s of one thing and 2s of other thing combines, I will form again one bonding corresponding to that, one anti-bonding corresponding to that. Again, same with P, right? So we will try to bring out the shapes of all these molecular orbitals, but that is not in the syllabus. It is not required also. But still, I'll just give you a gist, right? So we are going to see if at all two s orbitals or two p orbitals, or I will not go into D because D is very complex, right? So we are going to see how s orbitals and p orbitals undergo interference constructively and destructively to form a particular shape of bonding orbitals and anti-bonding orbitals. So we'll see what is that. Okay.
Sure, Doc.
Yeah.
So every molecule will have a bonding molecular orbital and anti-bonding molecule.
Yes, every orbital will not have one. They will have so many bonding orbitals, as many number of anti-bonding orbitals. But whether it has electrons in it is the question.
Okay, sir.
Right? Anyways, we'll see it. Don't worry. In a very short while, we'll look into it. Right? Okay. So let me take s orbitals. Okay, so I know s orbitals will be like this, two s orbitals. Okay, so now understand, assuming that they are going to undergo constructive interference, right? Say if they undergo constructive interference, right? So this plus does not indicate nucleus. Please understand, right? This plus, whatever I'm writing here, does not indicate your nucleus. It indicates on which part of the coordinate axis it is. So obviously, I know the entire s orbital is in the plus. Entire thing is plus, basically the positive axis, right? That's what it indicates. Whether it's above the axis or below the axis, that's what it exactly indicates, right? So you can even put negative and negative, no problem, because I know s orbitals are spherically symmetric, right? So, but no problem. This is does not have any sense here. This sign which I put inside the orbital doesn't make any sense. It just talks about whether the wave is above the axis or below the axis. That's what it indicates. You can even put plus plus or minus minus, doesn't matter, right? But if I go for p orbital, yes, it matters how you are putting the plus. You'll be putting in one lobe, the minus will be putting in another lobe, right? So that time it matters, but for s orbitals, it doesn't matter whether you put a plus or minus, right? So I'll just take plus and plus, right? Okay. So now, again, there can be two kinds of interference here. They will undergo constructive, they will undergo destructive. Say again, the sign will change. If I put a plus, it's constructive now, right? So now what do you expect to see? This is what you will expect to see. You will see a bigger wave like this, right? This will together to form a big wave like this, right? So obviously you can see that this basically the shape represents the electron cloud. Where is it, right? So you can see that the electron cloud is right in between the two. I would say if at all these two are the nucleus, it is in between the two nuclei, right? So this is what happens when I have constructive interference. This is how. So okay, I can give you some names, right? So please understand, people, right? So how I have sigma and pi bonds in your normal bonds, right? Say I know that sigma will have head-on collision, head-on overlap, and your p orbitals can, when I go to pi bond, I can have lateral overlap, right? Now same thing holds good here also, right? So s orbitals, obviously, okay, here also I have two other type, like one is bonding and anti-bonding. That is one type of classification. The other type of classification is whether it's going to be a sigma bond or a pi bond. That also matters. Okay, so obviously in the s orbitals will not be able to form pi bonds because they're spherically symmetric. They will not be able to undergo lateral overlap, right? So obviously in this case you will see that only sigma bond is possible. Okay, so how do I represent it? Say if at all this was one s orbital and another one s orbital, or then generally call it as s orbital only. Why one s? Okay, so I'll call it as an s orbital, right? It can be 1s or 2s, right? So now this, what will be the name of this orbital? Obviously, is going to be bonding, right? So I represent it like this. I represent it as sigma, the sigma bond, right? And obviously, what orbitals are combining? S orbitals are combining. So I write it as sigma s. This is how you represent this orbital, molecular orbital. And this is a bonding molecular orbital. If it is anti-bonding, I'll tell you. Next thing we'll see. Now this is constructive interference, right? So this is how I represent. And if at all specifically you want to mention which exact s orbitals are combining, you will be able to do that. Say if it is 1s and 1s, this is sigma 1s. If it is 2s and 2s, it is going to be sigma 2s, right? Like this will represent. Okay, cool. Now we'll see what happens when I have destructive interference. Hope you've taken this down. I'll give you 5 more seconds. Okay, fine. So now instead of this positive sign here, I put a negative sign indicating that I'm going to have destructive interference happening. Okay, fine. So now how the molecular orbital will look. So please understand that minus sign indicates that these two orbitals are going to go away from each other. They are going to repel each other, something like that, right? So you will see that, I don't want to put the axis here. You will see that I'm going to have something like this. This is what I see, right? So this is what is the shape of the orbital. You can see how different it is, right? So there I formed a bigger orbital. Now here they are moving away from each other. So where do you see the electron density? Electron density in the previous case was in between the two nuclei, right? But see where the electron is now. Here the electron is here in this space, and here it is in here in this place, right? So obviously this corresponds to your anti-bonding molecular orbital because it is destructive interference, right? Now the next question is, how do I represent it? This is how I represent. So guys, please understand, whenever you have an anti-bonding orbital, you have to put a star for that, right? So if it is bonding, it is sigma 1s. If it is anti-bonding, again it is sigma bond only. You can see that it is what is a head-on collision only. There's no doubt about it. So still it's a sigma, right? And still it is an 1s orbital. But how do I differentiate it between your bonding and anti-bonding? Just by putting a star, which is called sigma star 1s. So sigma star 1s is the anti-bonding orbitals when two 1s orbitals combine. And this is how the shape will look. Understood? So this is my sigma star 1s. Okay, fine. So we'll see what happens when I have p orbitals. Okay, we'll try to do that. Right. Cool. Again, guys, if you don't remember the shapes, very good. I mean, it's not very good. I mean, it's okay. It's completely all right, right? So because nobody is gonna ask you in your school exam these shapes, but again, you okay. Before all this, I give you advice. There is one important thing which I forgot, right? So guys, here I have a nodal plane, isn't it? Nodal surface. What do you mean by nodal surface?
Area
What do you mean?
where probability of having an electron is 0.
Exactly, right? So do you see that in this entire region, you don't find any electron? Isn't it?
Yes, sir.
So this corresponds to a nodal surface or nodal plane, right? So this is the main point of difference between your bonding and anti-bonding orbitals. Bonding molecular orbitals will not have any nodal plane, but definitely anti-bonding orbitals will have a nodal surface. That is one main point of difference between your bonding and anti-bonding. Last time you didn't see any nodal surface like this when I had constructive interference, right? So here definitely I'm going to have a nodal plane coming into the picture. Okay, fine. And yeah, so what I was telling is, if you can remember this, it will be very helpful for your competitive exams level. Yes, they might ask you sometimes the shapes, right? But even there, nobody is going to ask you the shapes as such. Like very rarely they will ask, even in your JEE or NEET exams. But anyways, knowing this is a very fundamental thing. It should have been important, but you know India, right? You know Indians, like that's how it is. Anyways, so move on. We'll see how p orbitals will have their shapes. Okay. So now, guys, there are 3 p orbitals, isn't it? Px, py, and pz, right? So you first have to understand, or you first have to decide which will be the internuclear axis, right? Which will be the internuclear axis. So if at all you decide that z-axis is the internuclear axis, you can actually decide anything. It's up to you, right? Say if you decide that the internuclear axis is z-axis, that means obviously out of the 3 p orbitals, only one of them can undergo head-on overlap. Say for example, if this is my z-axis, right? So I know p orbitals and pz will eventually be like this. That is, this is my z, or again I can have one more. This is my z-axis, right? So if I decide this, definitely px and py can only undergo lateral overlap. There is no case, there is no question of head-on collision. If I decide that z-axis is my internuclear axis, right? So you will first decide it, right? We'll decide that z-axis is my internuclear axis. So definitely pz can form sigma bonds, and px and py will only form pi bonds, because the already one head-on collision is over. So how can I, if at all there are px here, say for example px here, how will they undergo a head-on collision? They can undergo only lateral overlap. Same goes with py or p, whatever it is, right? So first we'll decide that the internuclear axis is pz, and we'll make sure that only pz, sorry, the internuclear axis is z-axis, right? And we'll make sure that only Pz can form the sigma bond, and Px and Py will form pi bonds. Is that okay? You can actually keep anything, it's up to you. But everywhere they follow internuclear axis as Z axis, and that's why we are also following, but there is no restriction, people. You can see, you can choose whatever you want, right? So anyways, this we have made sure that is Z axis is my internuclear axis. Okay. So let me take then PZ and PZ undergoing constructive as well as destructive interference. Okay. So now PZ, this is my Z axis, guys. Please remember, say this is plus and this is minus. You can see obviously, right, where the this is my origin line, right? And obviously this side it is positive, this side it is negative. That's what this plus and minus are indicating, right? Not the actual nucleus or whatever it is, right? So this plus indicates that it is above, that is positive axis. This is in the negative axis. Anyways, so now if I have constructive interference plus with another PZ, so again plus minus, sorry. Okay. So what should you do now? If I put plus, if it's constructive interference, the positive, negative will interact, isn't it? So this positive, this negative will interact, isn't it? So they are going to form what? A sigma orbit. Correct. Sigma molecular orbital, and we'll see how is it going to look. Right. So you will see that, and guys, please understand this. If I have plus and plus interacting, right, so they will come together to form a bigger plus, right? And you can see that the minus will not be able to interact at all, right? The minus, because it is in the farther end, right? So the plus and plus will interact to form a bigger plus, but the minus is not even interacting, right? Or you can say that minus and minus will interact to form a bigger minus, and the plus will not even interact, right? So either way, you will be able to see a shape like this. You will see that there's going to be a big plus and with two negatives on. Are you able to visualize what I'm saying? Right? So they are undergoing head-on collision. Right? Say plus and plus will interact to form a big plus. But look at these two minus, they're not even interacting. So they will be staying as such. Right? So I don't see any nodal plane here, isn't it? Just because it is going to be a bonding molecular orbital. I am not going to see any nodal plane. Now, how will I represent it? You tell me. Guys, what will be how will we denote this orbital? You tell me.
Sigma
So
PZ.
this is 2p and 2p, okay? This is 2p z and 2p z answering. So what is it, Rohan?
Sigma 2p.
Yeah, exactly, right? It is again, I know it's going to be a sigma bond because head-on collision, so sigma, and I know what orbitals are combining. 2p z orbitals are combining, and I will not put any star because it is going to be a molecular bonding molecular orbital. Okay, right? Cool. So now we'll see what will happen if I have destructive interference, right? So guys, please take this down.
So
Yeah.
even this 2p like pp orbital is even possible in pi bond also, no sir?
Correct. That's what you're going to see next. Next thing is that only. We'll see first
Okay,
destructive interference, then we'll go for pi orbit.
Like how do you even find out which comes in the sigma and pi in case of p and p orbital?
That's what I'm telling. If I have px, py, and pz, first you have to decide which is the internuclear axis, right? So now in this case, we decided that the internuclear axis is z. So obviously only pz will form sigma bonds, px and py will form pi bonds. Understood?
Okay, sir.
Right? Fine.
Sir,
You can
but it's
actually,
up
there
to
is
us,
no
no, sir,
restriction.
what to
Yeah,
select.
exactly. There is no restriction. Now in this case, you have decided z axis to be the internuclear axis. If I choose x axis to my internuclear axis, then this would have been sigma 2px. But by
Oh, okay, sir.
convention they use only z axis. But again, there is no restriction. You can use whatever you want. Okay.
Yeah.
Fine.
Okay, thank you, sir. Yeah.
Cool. Right. So we will see. Oh, destructive interference. I wouldn't have rubbed the diagram. Same thing only. plus minus plus minus. Now in this case, I'm going to have destructive interference happening. Okay, fine. So obviously the plus and minus will interact, and the plus and minus will interact, right? Both sides. How will it be formed? 1 second. Yeah, something like this. So guys, this is how I'm going to have the, so again, you know how to represent it. This is PZ, PZ, okay, 2PZ, 2PZ undergoing destructive interference, you know, and it's a sigma orbital still, again, head-on overlap only. So it is going to be called as sigma 2PZ star. Again, the star represents that it is going to be an anti-bonding molecular orbital. Again, what you saw in your sigma star 2p, sigma star 1s, right? You will see the same thing here. You will see a nodal surface, nodal plane or nodal surface or whatever it is, where the probability of finding an electron is 0. Understood, right? So very simple. They have destructive interference moving away from each other, repelling. That's what you need to understand. Okay, fine. So that's about your P, that is sigma piece, that is PZ as the internuclear axis, obviously P Z axis as the internuclear axis, and PZ will undergo sigma bond head-on collision, right? So we'll move on. So we have two more, that is your PX and PY. So if at all I see for either of them, because both of them are going to undergo only pi bond, that is lateral overlap, right? So we'll see if I see PX or PY, either one of them, other one is understood, right? So we'll see any one of them. If you have taken this down, right? Okay, so we are going to take Px people. So I will not be able to represent it like in the head-on collision. I have to represent it like this: plus, minus. Say this is my P, because this is y-axis, this is x-axis. We can keep. Say now constructive interference with plus minus, and this is my y-axis, this is my x-axis. Assuming, right? So obviously you can understand that they will not be able to undergo head-on collision. They have to undergo only lateral overlap, right? Okay, and it is constructive. Cool, right? Now this is how we are going to see the molecular orbital. Okay, fine. I'll give you that and then I'll explain. So you will see that there is going to be a big positive, big negative, and there is a nodal plane. Nodal plane, you do expect a nodal plane, isn't it? Because it is not head-on collision. Obviously, at the origin here and here, I don't have anything. Already I have a node, right? So obviously, in the origin, you will find a big node, right? Between the positive and negative, you will find a very, very big node. So the difference between your sigma and pi, the main thing is that if I have sigma molecular orbital, I don't have any node there. But if it is a pi molecular orbital, there is a node, right? So then, sir, you are confusing me. Even sigma star had what is that? Nodal surface, but there the nodal surface was perpendicular to the internuclear axis. You can saw you would have seen that, say if it is plus and plus, you would have seen that this would have been the nodal surface if it's an anti-bonding orbital, right? That is, if this is the internuclear axis, the nodal plane is perpendicular to the internuclear axis, right? But here what you see, it is parallel to the internuclear axis, or I would say this is vertical, this is horizontal, but that is a very crude way of saying it, right? You have to mention that if that is the internuclear axis, it is perpendicular to the internuclear axis, and in this case, if this is the internuclear axis, along the internuclear axis, I have a nodal surface, right? So again, how will I represent it? So this is Py undergoing constructive interference, and it's the pi bond, so I have to put pi, right? And which orbital are involving? 2py and 2py are involving, so it is pi 2py. This is how I represent the molecular orbital, bonding molecular orbital of pi 2py. Understood? This is how the shape will look. No problem. Now we'll see how destructive interference happens, right? And that's the last thing, right? You will not go for D or F or whatever it is because that is very complex beyond the scope of your 11th class, right? Now, if it is destructive interference, if it is destructive interference, right? So what is happening? What is going to happen? All the four lobes are going to repel each other, right? So I told you that if it is a anti-bonding orbital, right, you are definitely going to have some nodal plane. And since it is a pi orbital, right, definitely I'm going to have one more nodal plane. Please understand. Because of anti-bonding, perpendicular to the internuclear axis, one nodal plane. And since it is a pi bond, I will have along the internuclear axis also, I am going to have one nodal surface. There are going to be two nodal surface if it is going to be pi star, right? Pi star means what? Anti-bonding of pi, right? So how will the shape look? This is how the shape will look. So you have one bay. Okay. So plus, plus, minus, minus, they have repelled each other, right? So you can see, since it is a pi orbital, there is a nodal plane here along the internuclear axis. And since it's a pi bond, right, you are seeing that there is one more nodal surface perpendicular to the internuclear axis. So whenever you, so how will I represent it now? It is going to be called as pi star because it's an anti-bonding, and pi because lateral overlap. And you will see that it is going to be pi star 2py, and pi star 2py has two nodal surfaces, one perpendicular and one along the internuclear axis. Okay. So yeah, and same way I would have had px also, right? Again, px would have had the same shape, right? So guys, yes, these are what are the different molecular orbitals I can have. Sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, sigma 2pz, sigma star 2pz, pi 2px, pi star 2px, pi 2py, pi star 2py. So these are all the different types of bonding and anti-bonding molecular orbitals I have. Okay, right, cool. So this we understood, right? So obviously I'm going to place electrons inside all of them, right? So now, as I told you, all the three principles, that is Aufbau's principle, Hund's rule of maximum multiplicity, Pauli's exclusion principle, all these things you have to follow in order to fill the electrons in the bonding or molecular, anti-bonding molecular orbitals, right? So fine. So we'll see how and all we are going to have. I'll just take a very simple example for today. We'll continue with this in the next class. Like we have few more minutes left. Okay, fine. So first, since I'm going to follow Aufbau's principle, right? Since I'm going to follow Aufbau's principle, you have to understand what will be the energy order, right? What will be the energy order of the different molecular orbitals, right? This is what is the order. So you are going to have two different orders, right? Say now, see, please understand that we are not going to talk about the individual atoms electron. I'm going to take a molecule like H2, and H2 has totally how many electrons? One electron coming from each hydrogen, isn't it? So I'm going to speak about molecular orbitals. Please understand the term molecular speaks only about molecules. So you have to count the total number of electrons in that particular molecule, right? Then only you have to write the electronic configuration, right? So now first we'll see the energy order, or the order in which you have to fill, right? Okay. Say first starting with sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. It is sigma 2pz will come here. No. Right? So after this, after sigma star 2s, it is going to be pi 2px equal to pi 2py. So please look at this, right? Pi 2px and pi 2py have equal energies, right? So how you know how to, when you have degenerate orbitals, when you have, what do you mean by degenerate? Same energy orbitals, you have to follow Hund's rule of maximum multiplicity. For example, after filling all the electrons here, if you're going to come here, first you have to put 1, 1, then only you have to go for pairing 2, 2. Hope you remember this. Anyways, we'll see more and more examples at the time. So please understand that pi 2px and pi 2py are of same energies. So you have to follow, whenever you come here, you have to follow Hund's rule of maximum multiplicity. First singly put them, and then only pairing has to happen, right? Okay, so after this, I would have had sigma 2pz, then comes your pi star 2px equal to pi star 2py, right? And at last, I have sigma 2pz star. This is the order which you have to follow, right? First, starting with sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, pi 2px equal to pi 2py, right? And sigma 2pz and pi, and then after that the anti-bonding, sigma 2px equal to sigma star 2px equal to sigma star 2py, the anti-bonding of this, and lastly the anti-bonding of sigma 2pz, that is sigma star 2pz. Okay, right? Fine. So this order you have to remember, people. Right? This, there is no like, this is very simple, right? Obviously, s orbitals are already, I mean, 1s orbitals are having lesser in energy. So when they combine destructively or constructively or destructively, they will form lesser energy than when compared to 2s. Obviously, 2p orbitals are still higher, right? So obviously, this is very easy to understand also. Why is it like this? Okay. And please understand, this has to be followed when the total number of electrons is less than 15. Right? When the total number of electrons in that molecule is less than 15, only then you have to follow this. Right? If it is greater than 15, little modifications will be done in the order. Right? So that also will have. So when the total number of electrons is greater than or equal to 15, even if it is equal to 15, right? So then you will just write it like this: sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. Now the only thing which will you change is this and this. This you will interchange. That's it. That is sigma 2px and pi star 2px equal to pi star 2py. You will interchange, right? So you will see that I will have sigma 2pz first coming here, and then you have pi 2px equal to pi 2py, and this is nothing. This is nowhere it is changing. That's it. Only these two will remain as such. So you will have pi star 2px equal to pi star 2py, and at last sigma 2pz. I think you're not able to see. Right. So sigma star 2pz. So the only thing which is different between total electrons less than 15 or equal to greater than 15 is these two. Only these two are interchangeable, and nothing else is changing. Okay. Again, you'll ask me, sir, why this is happening? I'm sorry, you will, even if I tell you, you will not be able to understand. It is beyond the scope of this book or down this class. Okay, fine. So for now, just understand that this interchange has to happen. Okay. So what is the time? Okay, guys, I think we are done with this. So next class, like, you understood the concept of molecular orbitals, bonding, anti-bonding, the constructive, destructive, all the shapes, the nodes, all these things you saw today. So next class, we will just be filling electrons into this. Very, very simple, right? And after filling the electrons, whatever the shortcomings you found in your VSCPR and theory of hybridization, we will not be able to tell about the strength of the bonds, the color. Color, again, we'll not be able to speak here, but the magnetic properties, right? So whether the molecule will exist or not, all these things we'll be able to predict. Okay, so we'll see that how in the next class. So until then, we'll see you guys. Bye bye. Thank you.
Sir, next class will be finishing the lesson, no, sir?
Most probably, that is what I'm thinking about, but still it might shoot up also. But 95% next class, the chapter will be over. Okay. So
Oh,
in your
sir,
school,
can
how
you
is it
just
going?
send any notes?
Notes?
Sir? School, yeah, they came in this molecular orbital, sir.
Okay,
They
they are in
started it.
molecular orbital. Very good.
You said they completed
Bonding
till
axions.
where you taught for our exactly till here. They completed exactly till here, sir.
Oh, they completed exactly till here. Okay, okay. Fine, fine. Very good, very good. Anyways, did they explain all the
Like she
other
told
stuff?
some
Like,
hydrogen bonding.
oh, yeah, yeah. Oh, oh, oh,
Yes, sir,
oh.
yes, sir, everything is
Actually,
covered, sir.
it is not going to complete in the next class, people. We will have one more class. After that, next class, I'll have one more class because we didn't even speak about the secondary types of bonds. We are speaking still only about the primary types of bonds, like the coordinates, ionic, all these things. But we never went into the other side, the hydrogen bonding, Van der Waals forces, all these things are still there. So that might require one more class. So I will not be able to complete in the next class. Okay,
Yeah, okay, sir.
right? Cool. Till then, bye guys. We'll meet again.
Sir, is there any notes can you send for this lesson,
Oh,
sir?
notes. What can you do is notes. Okay, I'll see what I can do, but I don't think notes will be a good option. If at all your friends had taken notes, like in the class, you can ask them if they have taken notes, or if at all you didn't take notes, you can just fast forward the videos, all the videos which we have seen, and take down notes. That will be better.
Yeah, okay, sir. I'll see through it. Thank you,
Okay,
sir.
or you can buy a reference book for yourself, right? Buy a good reference book, right? From that you can study. Just mark the points there. From that you can study. Okay.
Yeah, okay, sir. Yeah.
Right.
Thank you, sir.
Nice.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.